Hello students, in this video we are going to learn about inverse Laplace transform. Last video we learned about the Laplace transform. One of the applications of Laplace transform is to solve the ordinary differential equation. Now when you apply this Laplace transform to the ordinary differential equation, the ordinary differential equation will be converted to algebraic equation in terms of S. Simplify that and then we apply the inverse Laplace transform. And that gives you the solution of the ordinary differential equation. Now, as we have learned this already, the tables of Laplace transform. The Laplace of 1 is 1 by s. Laplace of t raised to n is n factorial by s raised to n plus 1. Laplace transform of e raised to at is 1 by s minus a. Laplace transform of sine k into t is k by s square plus k square, and so on. You have to by heart this, then only we will be able to do the inverse Laplace transform. We know that Laplace of f of t is defined as integral 0 to infinity e raised to minus st ft dt. That is taken as capital F of s or simply capital F. So we can consider inverse Laplace transform as L inverse f of s is equal to f of t or simply small f. So Laplace of small f is taken as capital F and Laplace inverse of capital F is taken as small f. This figure you can see when small f we apply Laplace, you are getting capital F, and when you take inverse, capital F is converted to f, small f. Now small f is a function with variable t, whereas capital F is a function with variable s. Now this is a table of inverse Laplace transform. Inverse of 1 by s is 1. Laplace inverse of 1 by s minus a is e raised to at. Inverse of 1 by s raised to n is t raised to n minus 1 by n minus 1 factorial. Now 1 by s minus a raised to n is t raised to n minus 1 by n minus 1 factorial, and then here we apply the inverse shifting into e raised to at. 1 by s square plus b square is 1 by b sine bt. Inverse of s by s square plus b square is cos bt. 1 by s square minus a square is 1 by a sine h at. S by s square minus a square is cos h at. Ninth one, inverse of 1 by s minus a the whole square plus b square. Now you can see that is same as the sine formula. That is sine bt by b. There we apply the inverse shifting e raised to at. Then s minus a by s minus a the whole square plus b square. So this is of the form s by s square plus b square. That is cos bt. Then we apply the inverse shifting. You will get e raised to at into cos bt. 11 s by s square plus b square the whole square is 1 by 2b into t sine bt. Now if you by heart this 11 formulas, you can learn the inverse very fast. Now when you do the inverse Laplace transform, there are actually 6 methods. The first one is we have to check whether it is in the standard form. Second, inverse shifting. Third, making the denominator a perfect square. Fourth, if you are able to factorize the denominator, we will apply partial fraction. In some cases, you will get log, tan inverse, cot inverse, and so on. That is the inverse trigonometric function. That is our fifth method. And the last method is convolution theorem, applying convolution theorem. We apply convolution theorem when we have two standard inverse Laplace transforms. And we will discuss the 6 methods detailedly. The inverse Laplace transform. Laplace of small f is capital F, and the inverse of capital F is small f. Now consider an example. Laplace of sine 60, that is 6 by s square plus 6 square. Now the inverse of s6 by s square plus 6 square is sine 60. Or sometimes it may take like L inverse of 1 by s square plus 36. So that is 1 by s square plus 6 square. That is sine 60 by 6. We call the formula Laplace of t raised to n is n factorial by s raised to n plus 1. So for example, inverse of 7 factorial by s raised to 8. So s raised to 8 means n plus 1. So n is 7 here. So L inverse of 7 factorial by s raised to 8 is e raised to 7. Now consider another example. L inverse of 5 by s raised to 11. Now s raised to 11 means n plus 1 is 11. So n value is 10. Okay, and the numerator we should have 10 factorial, but 10 factorial is missing there. So we can write 5 into Laplace inverse of 1 by s raised to 11. We need 10 factorial in the numerator. So multiply 10 factorial in the numerator and divide by 10 factorial. So you will get 5 by 10 factorial, Laplace inverse of 10 factorial by s raised to 11. And that is t raised to 10. So Laplace inverse of 1 by s raised to 11 is t raised to 10 by 10 factorial. Now look at the next problem. Laplace inverse of 1 by s minus 1 raised to 11. Now when you do this, you have to remember 1 by s raised to 11 is t raised to 10 by 10 factorial. And then here we apply the inverse shifting. Instead of s minus 1, we have to write e raised to at. Here a is 1. So it is e raised to 1t. Now consider the second example. Laplace inverse of 1 by s minus 2 raised to 8. Now, when you do this, you have to remember 1 by s raised to 8 is t raised to 7 by 7 factorial. And instead of s minus 2, you have to apply the inverse shifting. That is e raised to a is 2 here. So it is e raised to 2t. So the third example, Laplace inverse of 1 by s plus 3 raised to 10. So 1 by s raised to 10 is t raised to 9 by 9 factorial. Now instead of s plus 3, we apply the inverse shifting and a here is minus 3. So it is e raised to minus 3t. So Laplace inverse of 1 by s raised to 11 is t raised to 10 by 10 factorial. Similarly, Laplace inverse of s by s raised to 11. So you can cancel 1s. It is same as Laplace inverse of 1 by s raised to 10. And that is t raised to 9 by 9 factorial. Now another important method having shifting also. Laplace inverse of s by s minus 1 raised to 11. Now in this case, s minus 1 is in the denominator. We have to make s minus 1 in the numerator also. So s minus 1 plus 1. Now separate the numerator. S minus 1 by s minus 1 raised to 11 plus 1 by s minus 1 raised to 11. So one of the s minus 1 will get cancelled. You will get L inverse of 1 by s minus 1 raised to 10 plus L inverse of 1 by s minus 1 raised to 11. Now the inverse of 1 by s minus 1 raised to 10, you have to remember 1 by s raised to 10. That is t raised to 9 by 9 factorial. And then apply the inverse shifting. Here a is 1, so it is e raised to t. Plus, when you do 1 by s minus 1 raised to 11, you have to remember of 1 by s raised to 11. And that is t raised to 10 by 10 factorial. And apply the inverse shifting. That is e raised to t. Another example of standard inverse transform. Now consider Laplace inverse of 7s plus 15 by s square plus 2. Now the denominator is of the form x square plus k square. Now here k is the root the whole square. So we can separate the numerator. 7s by s square plus 2, 15 by s square plus 2. 7 is a constant. You can remove that. 7 into Laplace inverse of s by s square plus root 2 the whole square. 15 is a constant. You can remove that. 15 into Laplace inverse of 1 by s square plus root 2 the whole square. Now that is in the standard. So directly you can write the value. 7 into cos root 2t. Now 15 into, and that is sine root 2t by root 2. Now let us consider one more example of the standard type. Laplace inverse of 1 by s square plus 49 plus Laplace inverse of 5s plus 3 by 9s square plus 16. Now the first part s square plus 49 is almost in the standard form. So we can rewrite that as s square plus 7 square. But the second part, 9s square plus 16, you get s square plus k square. So you have to remove the 9 from there. So let's take 9 common factor. We can rewrite that as 9 into s square plus 16 by 9. Again, we can rewrite that as 9 into s square plus 4 by 3 the whole square. Now the denominator is almost in the standard form. S square plus 4 by 3 the whole square, where k is 4 by 3. Now we have to rearrange the numerator. 5s plus 3, we can separate that as 5s by the denominator plus 3 by the denominator. Now 5 by 9 is a constant. Remove that. You will get L inverse of 1 by s square plus 7 square plus 5 by 9 L inverse of s by s square plus 4 by 3 the whole square plus 3 by 9 L inverse of 1 by s square plus 4 by 3 the whole square. Now take the inverse. Now the first part is sine. Sine kt by k, that is sine 7t by 7 plus 5 by 9 cos 4 by 3t plus 3 by 9 becomes 1 by 3, and that part is sine. Sine 4 by 3 t by 4 by 3. The next method is based on the partial fraction. If the denominator is factorizable and the degree of the numerator is less than that of the denominator, we can apply partial fraction. Here, the denominator is factorizable and the degree of the numerator is less than that of the denominator. The degree of the numerator is 1 and the denominator is 2. So we can apply partial fraction. A by s minus 5 plus b by s plus 2. In order to find a and b, multiply completely with the denominator s minus 5 into s plus 2 and cancel the common terms. So 3s plus 5 equal to a into s plus 2 plus b into s minus 5. Now to solve for a and b, compare both sides with the coefficients of s and the constants. You will get two equations in a and b. That is a plus b equal to 3 and 2a minus 5b equal to 5. And then you have to solve these two equations. And as we solve, you will get a is equal to 20 by 7 and b is equal to 1 by 7. Now we're going to find the inverse of 3s plus 5 by s minus 5 into s plus 2. That is same as L inverse of a by s minus 5 plus b by s plus 2. So a is a constant, take it outside. A into Laplace inverse 1 by s minus 5, b into Laplace inverse 1 by s plus 2. Now these are standard types. So 1 by s minus 5 is e raised to 5, and the Laplace inverse of 1 by s plus 2 is e raised to minus 2. After that, substitute a and b, that is 20 by 7 e raised to 5t plus value of b 1 by 7 into e raised to minus 2t. That's the answer. Now let's consider another example based on partial fractions. That is 3s plus 4 by s minus 2 into s square plus 7. The degree of the numerator is 1, degree of the denominator is 3, so we can apply partial fraction. So a by s minus 2 plus s square plus 7 cannot be further factorized. It is a quadratic. Therefore, the numerator you take bs plus c or bs plus b here by s square plus 7. So the partial fractions a by s minus 2 plus bs plus b by s square plus 7. Now to solve for a, b and d, multiply completely with the denominator, cancel the common terms. You will get 3s plus 4 equal to a into s square plus 7 plus bs plus d into s minus 2. Now the terms of s square, s are present, so we can compare the coefficients of s square, s and the constants. You will get three equations. A plus b equal to 0, minus 2b plus d equal to 3, 7a minus 2d is equal to 4. Now a plus b equal to 0 means a equal to minus b. Substitute in the second equation and the third equation and solve it. You will get a, b and d. Now you can use calculator to solve it. You will get a is equal to 10 by 11, and b is minus a, that is minus 10 by 11, and d is 13 by 11. Now substitute, you will get L inverse 10 by 11 by s minus 2 plus minus 10 by 11 s plus 13 by 11 by s square plus 7. Now, the denominators are all in the standard form. Only the second part, s square plus 7, you have to rewrite that as s square plus root 7 the whole square. And then separate the numerators. So, in the first term, 10 by 11 is a constant. You can take it outside. Do L inverse 1 by s minus 2 minus again 10 by 11 is a constant. L inverse s by s square plus root 7 the whole square plus the next term we have 13 by 11 as a constant into L inverse 1 by s square plus root 7 the whole square. Now everything is in the standard form. Directly you can write the answer. So 10 by 11, L inverse of 1 by s minus 2 is e raised to 2t minus 10 by 11, and that is cos root 7t. 13 by 11 into sine root 7 t by root 7. Before moving to the another method, just recollect the old one. Laplace of cos kt is s by s square plus k square. Now to find Laplace of e raised to at into something, we apply the shifting. Now in this case, Laplace of e raised to at cos kt. We have to write the Laplace of cos kt, that is s square by s square plus k square. Then apply the shifting, that is s is replaced by s minus a. So we will get s minus a by s minus a the whole square plus k square. So we are going to apply the inverse Laplace transform here. So L inverse of s minus a by s minus a the whole square plus k square. You have to remember the formula of s by s square plus k square, and that is cos kt. You write cos kt and apply the inverse shift. So you have to write e raised to 8. Same way, L inverse of k by s minus a the whole square plus k square. Now that is of the form k by s square plus k square, that is sine kt. And then apply the inverse shifting. You will get e raised to at sine kt. Let's consider a few more examples of inverse shifting. The first example, L inverse of 1 by s minus 3 square plus 16. We write that in the standard form. It is 1 by s minus 3 square plus 4 square. Now that resembles to 1 by s square plus 4 square, that is sine 40 by 4. And the term s minus 3 square shows the inverse shifting, that is e raised to at. Here a is 3, so you will get sine 40 by 4 into e raised to 3t. Now the second example, 1 by s plus 5 square plus 9. You have to rewrite that as 1 by s plus 5 the whole square plus 3 square. That is the standard form of sine. Sine 3t by 3, and s plus 5 denote the inverse shifting. E raised to, here a is minus 5, so it is e raised to minus 5t. Now look at the third example, L inverse of s plus 2 by s plus 2 the whole square plus 5. First of all, you have to convert to standard form, s plus 2 by s plus 2 square plus root 5 the whole square. That formula resembles to s by s square plus root 5 the whole square, and that is nothing but cos root 5t. And then s plus 2 terms represents the inverse shifting, so it is e raised to minus 2t. And the last one, L inverse of s minus 3 by s minus 3 square minus 16. The formula resembles to s by s square minus 4 square, and that is hyperbolic cos h4t. And corresponding to s minus 3, apply the inverse shifting, you will get e raised to 3t. Another type of Laplace inverse in which the denominator is not in the standard form. Also, the denominator cannot be factorized. In such a case, we apply the method of completing the square. Now, look at the denominator. It is s square plus 10s plus 34. It is not factorizable. So, consider the first two terms, s square plus 10s. Now, compare that with the formula of a square plus 2ab plus b square. A square plus 10s, compare that with a square plus 2ab. So b is 5 That is, we have to add b square and subtract b square. So s square plus 10s plus 35 is rewritten as s square plus 10s add b square, that is plus 25, subtract 25 plus 35. Now s square plus 10s plus 25, it becomes a perfect square. That is same as a plus b the whole square. That is s plus 5 square plus 9. So the denominator we have converted to standard form. Now we have a term called s plus 5 square in the denominator. So we have to mix s plus 5 in the numerator also. Before finding the inverse, we have to make denominator as same as in the numerator. This denominator contains a term s plus 5. The numerator also we have to make the term s plus 5. So for s, instead of s, you write s plus 5. So when you open the bracket, you will get 4s plus 20. So you have to subtract 20 in the numerator. So you can see there L inverse of 4 bracket s plus 5 minus 20 plus 1 by the denominator. So 4 into s plus 5 minus 19 by the denominator. Now you can separate the numerator. 4 into s plus 5 by the denominator minus 19 by s plus 5 square plus 9. Now 4 is a constant, you can remove that. L inverse of s plus 5 by s plus 5 square plus 3 square. Here minus 19 is a constant, you can remove that. L inverse of 1 by s plus 5 square plus 9. Now the first inverse resembles to cos 3t. And the term s plus 5, you have to remove that with the inverse shifting. That a is minus 5. So you will get 4 e raised to minus 5t cos 3t minus 19, and the second part 1 by s plus 5 square plus 9. That resembles to sine 3t by 3, and apply the inverse shifting. You will get minus 19 e raised to minus 5t sine 3t by 3. Let's consider one more example of the same type. L inverse of 6s minus 4 by s square minus 4s plus 20. Now the denominator is not factorizable, so we're making it a perfect square. S square minus 4s, compare that with a square minus 2ab. So b is 2 here. So you have to add b square and subtract b square. That is, add 4 and subtract 4 in between them. So the denominator becomes s square minus 4s plus 4 minus 4 plus 20. Now the first three terms is s minus 2 the whole square. Minus 4 plus 20 becomes 16. So you will get 6s minus 4 by s minus 2 the whole square plus 16. Now once the denominator is made in the standard form, we have s minus 2 in the denominator. We have to make the same term in the numerator also. Now 6s instead of s, you have to write s minus 2. Now when you open the bracket, you will get 6s minus 12. So you are taking an extra term 12 there. So you have to subtract 12 and add 12 there. So 6 into s minus 2 plus 12 minus 4. So the numerator becomes 6 into s minus 2 plus 8 by the denominator. Now it is in the standard form. Now separate the numerator. So L inverse of 6 into s minus 2 by the denominator plus L inverse of 8 by the denominator. Now 6 is a common constant. You can remove that. Now L inverse of s minus 2 by s minus 2 square plus 4 square resembles to the formula s by s square plus 4 square. And that is nothing but cos 4t. Now instead of s minus 2, you have to apply the inverse shifting. So it becomes e raised to 2t. Now the second part, 8 is a constant. 1 by s minus 2 square plus 4 square resembles to sine 4t by 4. Now the s minus 2 term, apply the inverse shifting, you will get e raised to 2. Now this is our fifth type, the functions involving log, tan inverse, cot, etc. Inverse trigonometric function. Use another formula. Laplace of t f of t is equal to minus f dash s. That is the formula that we are going to apply. Now consider this example. L inverse of log s plus 2 by s minus 3. So log s plus 2 by s minus 3 is our capital F of x. Now we're going to apply the formula. Laplace of t into f of t is minus f dash s. So it is minus of log s plus 2 by s minus 3 the whole raised to dash. We have to differentiate that. Now log a by b is log a minus log b. So we can rewrite that as minus bracket log s plus 2 minus log s minus 3 raised to dash. We have to differentiate it. So when you differentiate, you will get minus bracket derivative log is 1 by s plus 2 minus derivative log s minus 3 is 1 by s minus 3. Now open the bracket, you will get 1 by s minus 3 minus 1 by s plus 2. Now take inverse. So t f of t is Laplace inverse of 1 by s minus 3 minus Laplace inverse of s plus 2. These two are standard type. You can write that as e raised to 3t minus e raised to minus 2t. To find f of t divided by t, you will get e raised to 3t minus e raised to minus 2t by t. Another example of same type, Laplace inverse of tan inverse 2 by s. The same formula that we are applying. Laplace of t into f of t is minus f dash s. Here f of s is tan inverse 2 by s. Substitute that, you will get Laplace of t into f of t is minus bracket tan inverse 2 by s raised to dash. You have to differentiate tan inverse. Now derivative of tan inverse x is 1 by 1 plus x square. Same thing we are going to apply. It is minus 1 by 1 plus, instead of x we have 2 by s. So it is 2 by s square, that is 4 by s square, into the derivative of 2 by s. 2 is a constant. Derivative 1 by s is minus 1 by s square. So you will get minus bracket 1 by 1 plus 4 by s square into minus 2 by s square. Minus minus cancel. Take LCM and simplify. You will get 2 by s square plus 4. Now take inverse transform. So t into f of t is L inverse of 2 by s square plus 4. Now 2 by s square plus 4 is in the standard form, that is sine 2t. So f of t is sine 2t by t. Our last method is based on convolution theorem. Now we usually apply this method when we have a product of two standard inverse Laplace transform. That is, f of s and g of s are two standard Laplace transforms. Now, if L inverse of f of s is small f of t and L inverse of capital G of s is small g of t, then L inverse of f of s into g of s is given by integral 0 to t f of u g of t minus u d. First example based on convolution theorem. L inverse of 1 by s plus a into s plus b. We can rewrite that as L inverse of 1 by s plus a into 1 by s plus b. So 1 by s plus a is standard form, 1 by s plus b is also standard form. Let's choose 1 by s plus a as capital F of s, 1 by s plus b as capital G of s. So when you take the inverse of that, it is e raised to minus 8. So small f of t is e raised to minus 80, and the inverse of g of s is small g of t, and that is e raised to minus bt. Now since f of s and g of s are standard terms, we can apply convolution theorem. The formula is L inverse f of s into g of s, the integral 0 to t f of u g of t minus u d. Now f of t is e raised to minus 80. So substitute, you will get e raised to minus au. You have to replace t with u there. And g of t, replace t with t minus u. So it is e raised to minus b bracket t minus u d. Now since these are exponent, you can add the powers. So e raised to minus au minus bt plus bu into d. So this is what you get after adding the powers. So integral 0 to t e raised to minus au minus bt minus bu d. Now we are going to integrate with respect to u. So the integral of e raised to ax is e raised to ax by the constant a. So here, when we are integrating with respect to u, the coefficients of u is the constant. So it is e raised to minus au minus bt minus bu by the coefficients of u, that is minus a plus b, where u varies from 0 to t. Now substitute the upper limit and the lower limit. You will get e raised to minus at minus e raised to minus bt by b minus a. The last example, L inverse of s square by s square plus 1 into s square plus 4. Now we are going to rewrite that as two standard form, s by s square plus 1, s by s square plus 2 square. So I'm choosing f of s as s by s square plus 1, g of s as s by s square plus 2 square. Now the inverse of that is cos t and cos 2t. Now we're going to apply the convolution theorem. Write the formula L inverse of f of s into g of s, integral 0 to t f of u, g of t minus u du. Now when I'm going to substitute, I see g of t is cos 2t. T should be replaced with t minus u. That is going to be a little bit difficult. So I'm going to interchange f of t and g of t for the convenience. So I'm going to take f of t as cos 2t and g of t as cos t. So I'm going to rearrange and substitute integral 0 to t. Instead of f of t, I'm going to write cos 2u. Instead of g of t, I'm taking cos t. So it is cos t minus u d. Now, cos A cos B is cos A plus B plus cos A minus B by 2. Apply that formula. You will get integral 0 to t cos 2u plus t minus u plus cos 2u minus t plus u by 2. Simplify that. You will get cos u plus t plus cos 3u minus t by 2. Now integrate. 1 by 2 is a constant, remove that. Integral of cos is sine u plus t by the coefficient of u, that is 1, plus cos 3u minus t, integral is sine 3u minus t by the coefficient of u, that is 3, where u varies from 0 to t. Substitute the upper limit and the lower limit and simplify, you will get 4 sine 2t by 6. Thank you.